Okay, guys, we're starting chapter 5, our last chapter, and we're going to talk about systems of equations in this chapter. Okay, so if we have a set of equations, in other words, more than one equations that we're considering at the same time, right, for the same problem, we call it a system of equations. And to be a solution of the system, then the solution must satisfy every one of the equations in the system. If all the equations are linear, then we call it a linear system. So if all the equations are linear, that means that their graphs make a straight line, right? So there's three options. They could intersect and we get one solution or a point that's on both lines. Or they could be parallel lines, and therefore we'd get no solution because there's not going to be a point on both lines. Or they could in reality be the same line, just look different. Think about this: if I divided this equation by 2, it's really the same equation. And therefore there'd be an infinite number of solutions because every point on one line would be a solution to the other line or to the other equation. So we could solve these systems by graphing. But now that we're back to just, hey, I've got a solution or no solution or an infinite number of solutions, then we don't have to graph. Remember, we started graphing because if I just had this one line, there's not a solution. I have all kinds of combinations of x and y values, and I couldn't list them all. But now we're going to go back to having a solution. So I've got a couple of methods I can use. Okay, one's called the substitution method and one's called the elimination method. Okay, you might also hear this as addition method. This book calls it elimination. Technically it's elimination by addition, so sometimes you'll hear it as just the addition method. But in the substitution method, we're going to solve one of the equations for one of the variables and then substitute it into the other equation. In the elimination method, we're going to make the coefficients on the same variable in each equation the same. One be a plus and one be a minus so that I can add them together and eliminate one of the variables. So if that sounds crazy, after we see a couple of examples, it should be clear. So let's look at some examples. Now this one says solving a system by substitution. So they expect you to do this by substitution. What I would like us to do is just do it by the easiest method possible. But let's go through the steps of solving it by substitution. Okay, if I'm going to solve it by substitution, that means I'm going to take one of these equations and solve it for one of the variables. It doesn't matter which one, but I definitely want to make it the easiest choice. So in my opinion, it would be easier to solve this for y, right? Because the y is already by itself. If I solve up here for x or y, I'm going to have to divide by 3 or 2 to get rid of that coefficient. And I'm going to create fractions in my equation. Here the x is negative, so the y looks good. It's already a positive y, and all I have to do to solve for that y is add x to both sides, so that this equation now becomes y equals x plus 3. 3 plus x doesn't matter. But now that I have one of the equations solved for one of the variables, I can take this equation and I can plug it in to the other equation and replace y with x plus 3. Because we know from the other equation y is x plus 3. Now remember, the reason we're having to do this to start with is because if I have an equation with 2 variables in it, I can't solve it for a numerical answer, right? I can't solve that for a numerical answer. Okay, so that's the reason I'm trying to make an equation that has either all x's or all y's so that I can solve it. So now I'm going to rewrite this equation. And I'm going to make it 3x plus 2. But instead of times y, y is x plus 3. Okay, and then finish the equation equals 11. So these equations are the same. 3x plus 2y equals 11. Now notice I got an equation with just one variable in it. So I can solve it. Let's first step, get rid of those parentheses. 3x plus 2x plus 6 equals 11. Okay, so combining like terms, 5x plus 6 equals 11. Okay, move the 6 to the other side because it's just a linear equation. 5x equals 5. Divide both sides by 5. And so I know x equals 1. Now, once I have a value for one of the variables, I can plug it into either equation and get the value for the other variable. The easiest place to plug it in will be right here because we've already solved it for y. So if x is 1, y is 1 plus 3, or y is 4. Now, they're going to ask you to leave your solution as an ordered pair, right, or as a point. So be careful of where you put your x and your y. That matters. So these two lines intersect at the point 1, 4. And therefore, that makes it a solution to both equations. You could easily check, plug it into both equations, and make sure it satisfies each one. Okay, that's our substitution method. Now, this one doesn't say do it by elimination, but just to see the difference, let's also do this by elimination. I'm going to rewrite the equation down here so that we can see them up at the same time. Hopefully I'll have enough room. Now the elimination method is based on the fact, again, that I can't solve either of these equations because each of them has an x and a y value. So if I were to eliminate one of those variable terms, then I'd have an equation with just one variable in it. Okay, so just think if we had equations like 1 plus 2 equals 3 and 3 plus 2 equals 5, I can add them together and get another true equation. 1 plus 3 is 4, 2 plus 2 is 4, 5 plus 3 is 8. Oh yeah, I'll get another equation. So that's what I'm going to do here. That's why I've drawn a line. I'm going to add them together. Okay, and I'll get another equation, but it doesn't help me to add them together as they are. I would get 2x plus 3y equals 14. I still can't solve it. But and I notice here that the x value is positive and negative. Remember, this is an equation. As long as I do the same thing to both sides, I can multiply by whatever I want. So if I were to multiply this equation by 3 all the way across, right, just multiplying by 3, notice then that when I combine these equations, add them together, 3x minus 3x gets eliminated, and I wind up with 5y equals 11 plus 9, 20. So dividing by 5, I get y equals 4. Oh yeah, y equals 4. And then I can go back and plug in and get x. So that's our two different methods. The vast majority of times, the elimination method is easier, but the substitution method, has its purpose. What if it's already solved for y? Okay, then it'd be easy to just plug in and go. Now over here, they both have to be the x and y on one side of the equal sign and the constant on the other. All right, so let's try this again. And this time it asks us to actually use elimination. Okay, so I look, and if I added these together, it wouldn't help me because I'd have 5x minus y equals 13. I still couldn't solve it. So I'm going to try to eliminate one of these variables. It doesn't matter which one, but a couple of things I'm going to look for Does one already have a plus and one a minus so that I don't have to mess with signs, because signs is where I'm going to make a mistake probably. Okay. Or I might choose the smallest numbers to keep my numbers as small as possible. So I've got a couple of choices. I could either multiply this whole equation by 2, making this a 6x. But then when I multiplied this one, I'd have to multiply it by -3, the whole equation by the same thing, to make a -6x. This is already a positive and a negative, so I'm going to try to make these the same number, right? So that when I add them together, they get eliminated. And that number will be 12. So to make this a 12, I need to multiply everything by 3 all the way across. A lot of times people forget to go over here and do the constant. And then this one, I need to multiply by 4. Don't have to worry about negatives here, so that's good. Don't forget to go all the way across. Now, that makes this equation 9x minus 12y equals 3. And this one, 8x plus 12y equals 48. Okay, just an idea why we want to try to keep our numbers as small as possible. Now, adding them together, I'll notice that this is going to add to 0 and get eliminated. So 9x plus 8x is 17x equals 51. Okay, dividing by 17. Then we have x equals 3. Once you have one of the variables solved for, you can go back and plug into either equation. Okay, doesn't matter what. Let's let x be 3 in this first equation. So we'd have 3 times 3 minus 4y equals 3. Okay, so 9 minus 4y equals 3. Let's subtract 9 from both sides. It doesn't equal 3, it equals 1. Okay, plugging into this equation right here, right? 3x, the original equation, minus 4y equals 1. Okay, so 3x minus 4y equals 1. 9 minus 4y equals 1. So subtract 9 from both sides. Negative 4y equals -8. Dividing by -4. Y equals 2. So my solution is the point 3, 2. X is 3, y is 2. Okay, what if we're given a system that looks like this? Don't even think about keeping those fractions. Remember, these are equations. So, oh yeah, anytime we have an equation, any kind of equation, first step is let's get rid of the fractions. So to get rid of these fractions, I'm going to multiply everything by 6. Okay, that means 6 divided by 2 is 3. 6 divided by 3 is 2. So this equation would be, let's put it right here. This equation would be 3x plus 2y equals 24. Okay, I need to multiply this by 2. Don't forget to go all the way across to get rid of those fractions. So this time they just completely cancel, and we get 3x plus 3y equals 30. Now these are the two equations that I'm going to try to solve. Okay, so I'm going to try the elimination method, and look, it's very nice. These already have the same coefficient. I just need one of them to be negative, right? So that when I add them together, they get eliminated. It doesn't matter which one, but I do notice, I try to make my math as easy as possible. So I notice that if I make this a negative, that this will be positive and this will be positive. So let's multiply -1 all the way through this equation, multiplying by -1. Then when I add them together, this is 0. 3y minus 2y is y. 30 minus 24 is 6. I already have the y value. I've just got to figure out the x value. Okay, so I'm going to plug it in maybe this top equation. Okay, I'm going to plug it in this bottom one even though numbers are bigger, just so I make sure and plug it into the original equation. I've changed some stuff up here. All right, so 3x plus 3 times y, which is 6 now, equals 30. So 3x plus 18 equals 30. Subtract 18 from both sides. All right. So 3x equals 12. Divide by 3 tells us that x equals 4. So my answer is the point 46. Okay, typically if you're pretty fresh out of high school, I think they do systems a lot in high school. So hopefully we won't have any issues with these. If you do, be sure and let me know. Okay, so this one gave us a clue. It says solving an inconsistent system, but let's see what that means. Again, it's set up nicely for the elimination method. Okay, they both have a plus and a minus. Here's my smallest numbers, so I'm going to multiply this equation by 2. That would give me a -4 and a +4, and keep my numbers as small as possible. So if I multiply all the way across by 2, okay, this equation would now become 6x minus 4y equals 8. And now here's the 2 equations I'm solving. So, both variables get eliminated. 0 plus 0 is 0 equals 15. So if in the process of solving these equations, if one of your variables, and not one, but if both of your variables get eliminated, that's your clue that, oh, remember, we had either we're going to get an answer or no answer, or they're really going to be the same line and we'll get an infinite number of answers. Okay, so these two are determined if both variables get eliminated. Okay, if you get like we did on the previous, what did we do, 3 problems at least, you get x equals a number, y equals a number, you keep going, right? And then you get your x and y. The second you get an equation with no variables, you know it's one of these 2 options. And how do you tell which one? Does this make sense? Is this true? Does 0 equal 15? No. That means there's no solution, right? No solution for this system. They're parallel lines, and we call that system inconsistent, right? There's not an answer to it. It's inconsistent. Had we got something true, like 15 equals 15, and I'd say, oh yeah, that's true. That's true all the time. That would mean it's this. It's actually the same line, right? And we'll talk about, probably in the next one, how to leave our answers for that. Yeah, with infinite many solutions. Okay, so same thing. I'm going to multiply this bottom equation by 2 because I have a -2 here, and if I make this a +2, okay, then I wind up with -8x plus 2y equals 4. And if I were to add the other equation to it, I'd have 8x minus 2y equals negative 4. And when I try to add these together, 0 and 0 again. So I have 0 over here. My variables got eliminated. It's one of those two conditions. Oh, I got 0 equals 0 this time, which is always true, always true. So this is all real numbers. Okay? So we're going to leave our answer still as a coordinate with leaving just one of the variables arbitrary, right? One of the variables arbitrary. So let's say if we were to leave x arbitrary, and pay attention to, it will probably tell you which variable to leave arbitrary. I'll do it both ways so we can see it. It doesn't matter. So if x is going to be arbitrary, right? If x is going to be arbitrary, then we're going to take one of these equations, okay, and solve it for x. So let's just take this one. So if I take this equation and solve it for x, okay, let's solve it for y. We need an x. If I'm going to make x arbitrary, I need an x in both equations, right? So let's solve this for x. So negative 4x, let's subtract y from both sides, equals 2 minus y. Let's divide everything by negative 4. You can do the whole thing or you can do them individually. Doesn't really matter. So x equals negative 1/2 plus y over 4. I was right to start with because I want an x in each one. I don't want to solve that for, I want to solve it for y. Right. Because I'm looking for y. All right. So let's solve this. Sorry about that, guys. For y, all I have to do then is add 4x to both sides. That made it a lot easier too. That's why I chose that one to start with. Okay, so y equals 4x plus 2. So I just put that in here as y, right? That makes sense. I don't know what I was thinking. Y is 4x plus 2. So now we have x, and y is 4x plus 2. Our key is we want these to have the same variable, right? Whatever we solve is arbitrary. So we can get any points we want. Let's say x is 3. If x is 3, then 12 plus 2 is 14. Oh, there's a solution. If x is 1, 4 plus 2 is 6. There's another solution. So when I write my solution like this, I can get any particular solution I want. We could have just as well have made y arbitrary, which would have meant it would look like this. And I want something here where x equals something with y in it, right? Both of these would need to have y. So here's where I would need to solve for x. All right, so let's subtract y from both sides, back to where we were. Negative 4x equals negative y plus 2. Divide by negative 4. I'm just going to do it like this for sake of easiness. So negative y plus 2 over negative 4. All right, so if y, let's just see if we get the same thing. If y is 6, and I plug in over here, negative 6 plus 2 is negative 4 over negative 4. Yeah, right? Or if y is 1, we would get 2 minus 1, negative 1/4. So once again, here's how we're going to leave our answer. Not both ways, but pay attention to whether the instructions ask you to leave x arbitrary or y arbitrary. If it says leave x arbitrary, they both need an x in it. If it says leave y arbitrary, they both need a y in it. Okay, we could have 3 unknowns, right? If you have 3 unknowns, though, you need 3 equations. Just like if we have 1 unknown, all I need is 1 equation, 1 variable. Then I can solve it with 1 equation. Once we jump to having 2 variables, then I had to have 2 equations to get back to a solution, right? Otherwise, if I had 2 variables, I had an infinite number of solutions and I had to draw that graph. But if I had 2 equations, hey, we were back to getting a possible a solution. If I have 3 equations, I need 3 variables. If I have 4 equations or 4 variables, I need 4 equations in order to solve it, and etc. But the same thing that can happen if we have an equation with an x, y, and z, those describe planes. So they could still intersect, 3 planes could still intersect in a way that there is a single point that's in all planes. Or you could get infinite many solutions. Look how they could intersect like this, and there'd be an infinite number of solutions. There could be no points in common. They could all be parallel and none of them intersect. Or, a couple of them could intersect, but never all 3 of them intersect. Another way, there could be no solution. Remember, to be a solution, it's got to satisfy all 3 at the same time. Or they could, in reality, all be the same plane. So I still have my same possibilities. I'm going to get a solution, or infinite number of solutions, or no solution. All right, here's the steps for solving a system of equations with 3 variables. So you might want to jot these down. I think it's easier to just go ahead and plow in and show you the steps as we go, but it'd be nice to have this written so you can see that this is what we are doing. Okay, so I notice that not only do I have 3 equations, but I have an x, a y, and a z. Okay, so first step, I'm going to take 2 of the 3 equations, any 2, and eliminate one of the variables. Okay, it doesn't matter which 2 equations and it doesn't matter which variable, but I'm going to look, before I decide that, I'm going to look at all 3 and decide which one would be easiest to eliminate, because my second step is I got to take that other equation and eliminate that same variable. So either, these would be all really easy. If I combine these 2, I could easily get rid of the x by multiplying by -2, and then I could come back and do these 2. Okay, here this would be easy to get rid of, and then one step here. I'm going to choose the z's just because one of them's negative. It keeps me from having to deal with a negative. So the first thing I'm going to do is I'm just going to take any 2 of the equations. So I'm going to take these 2 and add them together. Right? I only can do this because these are automatically eliminated. So 3x plus 2y equals 4. Notice minus z plus z, my z's got eliminated. So my next step, I need to take this one and either one of these. It doesn't matter which one. I'm going to do this one simply because it's already negative. So now I'm going to take these 2. Okay, so that gives me 3x plus 9y plus 6z equals 3. And trust me, you'll want your line through your z's here. Okay, and if I multiply this equation by 6, that'll eliminate the z. A mistake a lot of people make is when they do this, they eliminate maybe the z here and the y here. They're just not paying attention to what they're doing, and then they're stuck. Right? You got to eliminate the same variable. So multiplying this whole equation by 6, we would get 12x plus 6y minus 6z equals 12. When I add these together, the z's are eliminated again. So 15x plus 15y equals 15. Okay, so now at this point, I've got 2 equations, right, with the same 2 variables. So we're just like we were, right, in those previous examples. So I can combine these and solve for one of those variables. Now, I notice this one all has coefficients of 50. I could keep them. It doesn't matter. But anytime I can make my numbers smaller, it really helps me make my math easier. So if I see that they have a common factor, I can divide out and just make this x plus y equals 1. That's a much easier equation to work with. Now, I'm going to multiply this equation by -2 because just because it's the smaller number is the only reason I chose that, right? The smaller number, it'll keep my numbers smaller. So if I multiply this whole equation by -2, okay, and then put it over here, I have -2x minus 2y equals -2. So when I combine them, my y's get eliminated, and I have x equals 2. Okay. Once I get one variable solved for, I can plug back in, but I've got to kind of work backwards. It doesn't help me to plug in x equals 2 into any of these. I would still have a y and a z. So plug it into one of these equations that just has an x and a y. This one's the easiest, so I'm going to plug it in there. Okay, so if x is 2, I have 2 plus y equals 1. Or now I know that y is -1. Now that I know x and y, I can plug it into one of these. I'm going to plug it into this bottom one. So 2, since it's -1, I can just, instead of putting plus -1, I'm just going to put -1 plus z equals 2. So 1 plus z equals 2, or z equals 1. Now, x, y, x, y, z. There's your solution. And that should satisfy any one of those three equations. X is 2, y is -1, z is 1. Okay. Let's try that again. Okay, any 2. So I look at my x's. That wouldn't be bad. That wouldn't be bad. None of them would be terribly hard at all to eliminate. So I'm going to pick either the y's and the z's because some of them are already negatives. Okay, let's do the y this time just because we did z last time. So I'm going to take these two. I'm going to multiply this equation by 2. So I'd have a -2y and a +2y. So writing that one first, I have 3x plus 2y minus 2z equals 4. And if I multiply all the way across by 2 here, I would have 2x minus 2y plus 6z equals 10. Adding them together, my y's get eliminated. So we have 5x plus 4z equals 14. Okay, now I have to use this one, but it doesn't matter which other one I use. So I'm going to use this one along with this one just because it'd be an easier. If I use these two, I'm going to have to multiply both of them by a number. This by 2, that by 3. But if I use this one, all I have to do is multiply this bottom equation by -3, right? Because they're both negative, I need to change that sign also and get the 3 in there. So the top one's going to stay the same. But this one I'm going to multiply by -3. So -3x plus 3y minus 9z equals negative 15, multiplying everything by negative 3 so that these get eliminated. So 4x minus 3y is x minus 8z equals negative 6. Okay, notice now I have two equations that have an x and a z, so I can combine those. The easiest thing to do would be to get rid of, well, this, I could multiply this by 2. Okay, I started to say I'm going to multiply this by negative 5, but then I noticed, oh, multiplying by 2 would be easier and keep my number smaller because I'd get up to a 40 here. Either way is pretty easy, so whatever you want to do, but I am going to multiply this by negative 2. Okay, no, I'm not. I'm going to multiply this by negative 2. I'm going to multiply this by negative 2. Okay, so negative 10x minus, I'm not even going to do negative 2. Good lordy. Okay, all right. Let's see if we can get this eventually. Multiplying by 2. Okay, so 10x minus, no, just multiplying by 2, right? So plus 8z equals 28. Oh, double check myself. 10, 8, 28, all positive. Yes. All right, so my z's get eliminated. 11x equals 22. Okay, divided by 11. So x equals 2. Once I find out one of the variables, plug back in to find the others. And I need to plug in one of these equations that only has an x and a z in it. So what do you think? This one doesn't really matter. But I'm going to plug into this one. So if x is 2, we have 2 minus 8z equals negative 6. So subtracting 2 from both sides, we have negative 8z equals negative 8, or z equals 1. Now that I have x and z, I can plug in up here. I'm going to plug in this bottom one where my numbers seem to be smaller. So 2. Now y is what I'm looking for, so I'll leave that in there. Plus 3 times 1 is 3 equals 5. So 2 plus 3. Now I have negative y plus 5 equals 5. It looks like y equals 0 then, right? So my solution is 2, 0, 1. X is 2, y is 0, z is 1. Okay. Okay. Now, just like when we had a system with 2 variables, we could have still had no solution or an infinite number of solutions. And the way I determine that is the same. I just keep doing those same steps we just did. Excuse me, those same steps we just did. And if in the process of combining anywhere along the way, those 2 equations, I would get my variables disappear, then I know, oh, it's either a no solution or all just the same thing. Another way I can tell, if I have 3 variables but only 2 equations, I know my answer is going to be an infinite number of solutions. So I already know that here. Just like if I had 1 equation with 2 variables, it's an infinite number of solutions. I'd be drawing that graph. All right, so I know what I'm looking for. Let's see how we're going to leave our answer with these things. All right, so same process. I'm going to eliminate the y's. Either the y's or z's would be easier. All I'd have to do is multiply this by 4. right? But down here, I just have to multiply by 2, so it keeps my number smaller. So this one's going to stay the same. And I'm going to multiply this equation by 2. Okay, that means my y's get eliminated, and I wind up with 7x minus 7z equals negative 14. Okay, I'm going to, just to make all my math easier, I'm going to make that x minus z equals negative 2. Okay, now notice I used I don't know what makes it do that. Stop it, stop it, stop it. Let me. Okay, better. Now notice I've already used both equations. I don't have another equation to use. So I can eliminate another variable. Okay, so typically on these, again, you can leave any variable arbitrary, but we usually leave z arbitrary. So that means our answer is going to be something, something z. Right? So I just have to figure out what these are. Okay? Right here, I can already get the x value. So I'm just going to solve for z. Right? So I'm going to take this equation, solve it for z. Negative z equals negative x minus 2, right? If I subtracted x from both sides. Okay, divide or multiply by negative 1, so I know that z equals, why do I keep doing this? I'm going to solve it for x. I want to leave my z in there, buddy. All right, so I'm going to solve it for x. So I'm going to add z to both sides. So x equals z minus 2. So that's going to go right here. And now that I know x and z both in terms of z, I can plug into one of those other equations. Let's take this one where everything's smaller and I don't have a bunch of negatives. And instead of x, I'm going to put z minus 2. And then y is what I'm still solving for, right? Using this equation right here. And then plus z, which is just z, equals 4. And solve it for y in terms of z. So if I combine these terms, I'll have 2z minus 2 plus 2y equals 4. Okay, solving it for y, let's add 2 to both sides. So we have 2z plus 2y equals 6. So 2y equals minus 2z plus 6. And if I divide everything by 2, I'll get y equals negative z plus 3. So that's my y, negative z plus 3. You could do that leaving anything arbitrary, right? Any one of them that you want. So pay attention to what they ask you to leave arbitrary. It's usually the z or the y. The last one is usually what we do. Okay, all right. I hope that made sense. I know I keep flipping that stuff around. I'm sorry about that. All right. Applications with 3 unknowns usually require solving a system of 3 equations. Duh. Okay. Okay, if we know 3 points on the graph, we can find the equation of a parabola in this form. Look, what we don't know is an A, a B, and a C, right? But here we have a point xy, a point xy, a point xy. So I can plug in to this parabola here when I let x equal 2 and y be 4. So my first equation, I'm going to do it like this, just so it's in the order that we want it in, right? Just flip it around. All right, so if x is 2, then I would have a times 2 squared is 4, and again, I'll write it like this instead of a4, right? Same thing. Okay, plus if x is 2, then I'd have 2b, b times 2, 2b, and then plus c equals y is 4. Do the same thing here. If x is -1, -1 squared is 1, so I'd have a, and -1 times b would be -b, plus c equals y is 1. Okay, here we would have if x is -2, that would be 4a again. Okay, and then -2b plus c equals 5. And notice how I get 3 equations with 3 unknowns. Okay, I notice that these two, if I add them together immediately, that b gets eliminated without having to do anything. So I'm going to do that. So I'm going to have 4a plus 2b plus c equals 4, and 4a minus 2b plus c equals 5. Adding them together, the b's get eliminated, and we have 8a plus 2c equals 9. Now I've got to use this one, and so I'll use it with this one just because I don't have to change the signs on anything. All right. So this one's going to stay the same, 4a plus 2b plus c equals 4. This one I'm going to multiply by 2. 2a minus 2b plus 2c equals 2. Adding them together, the b's get eliminated again, and I have 6a plus 3c equals 6. You want to divide this by 3 so that we have 2a plus c equals 2. Now let's eliminate c, right? Let's eliminate c by multiplying this by -2. So -4a minus 2c equals -4. So we wind up with 4a equals 5. So a is 5/4 if we didn't make a mistake, right? I'm going to check my math. We can have fractions, of course. You're going to have fractions. But when I do, first thing I'm going to do, or if I get something crazy, first thing I'm going to do is check all my math. Okay, so 4a plus 2b plus c equals 4. 4a minus 2b plus c equals 5. 8a plus 2c equals 9. Okay. 4a plus 2b plus c equals 4. 2a minus 2b plus 2c equals 2. 6a, 3c, 6, 2, 1, 2, -4, -2, -4. Not a mistake, it looks like. Okay, or else I made the same mistake again. All right, now that I know what a is, I can find out what C is, maybe from right here, right? So let's get us some room. I'm going to go up here. Okay, so if A is 5/4, then I have 2, right, times 5/4. 5/4 plus C equals 2. So 5/2 plus C equals 2. I can get rid of that fraction by multiplying by 2, or I can just combine those fractions if I want, since it's already C. A lot of us have trouble with that. So this is an easy way to always think of it. All right, so 5 plus 2C equals 4. So 2C equals -1. So C is -1/2. All right, there's A and C. Now we can plug back in right here and get B. Since we've run out of room and we kind of know what we're doing, I'm not going to go to the trouble to do that. But then once you get A, B, and C, there you are. You plug in A, you plug in B, and you plug in C. And you have your quadratic equation that you were looking for. Okay, so let me know if you need anything. See you next time.